Hey, this is Eugene and Mike, Josh, Chad, and Sheriff. We're here together on another weekly episode of Live Contracts. And today is a Berry Club special.
Exciting.
Um, so today we're going to talk about Berry Club contract. And the interesting part about this is life upgrade that happened and how we actually updated an existing state by adding a banana berry. So let me present you first the Berry Club itself. So Berry Club is a demo app that I built to demonstrate what Near Protocol is allow us to do. And so Berry Club allows you basically to draw pixels on a board and the board getting updated. And as you can see, I don't have avocado. The way it works, when you join with the wallet, and I'll join with my different account. So when you join a login with the wallet, you get access key to this front-end application, a limited access key that allows you to call Berry Club contract. And in this case, the Berry Club contract has a public board where everyone can draw. And you can later draw pixels on the board, and the contract records them internally. You can buy avocado token with near, and that allows you to draw more pixels. For every pixel you draw, you pay one avocado token, and then there's now a farming preferences that allows you to farm either avocados, which allows you to draw more pixels, or bananas, which is a fungible token on this contract. So I will not go into more details on how this works, but it works through RPC. So RPC calls, like the front end calls RPC to get the latest board and refreshes it occasionally. And it does this efficiently to not fetch data that it doesn't need. So let's go into the contract to explain the basic details. Okay. The contract is, so this is the version of the contract before the upgrade, and it only has avocado, and you can only farm avocados. So when you draw something, it generates avocado. For every pixel, it generates one avocado a day. The avocado is a fungible token. It's split into a precision, so you can have a partial avocado. And the contract doesn't really care about the storage as much because you cannot send avocado, so you cannot really abuse the storage as easy. You need multiple accounts. So as usual, we have a main structure. It's called place. It has a map of account indices. So it's slightly different from usual where we have account ID to some account structure. Instead, it relies on given an index, U32 index for every account, unique account. So when someone else joins for the first time, they get a next index available. Then we have a board which stores pixels and ownership of pixels. Then we have list of account, a vector of account. This is also a persistent vector. And when a new account joins for the first time and draw its first pixel, this account is added to the end of this vector, and account ID is added to list of indices. Then there's some extra data for statistics. When this contract was first deployed, then total amount of avocado purchased and total amount of avocado burned to draw. This is the standard default. And when it's first initialized, it creates an account for itself and assigns all pixels to itself. There's one method to buy avocado, and the way it works, we grab the account by ID. This either returns an existing account or creates a new account. Then it calls internal method to buy tokens and records how many tokens for bought, saves the account. And there's another method which is draw. But to get into draw, we first need to figure out how that data is stored. For this, we have pixel board, which is initialized with pixel board new. So this is just an internal structure. It has a persistent vector of lines. So we store the pixel board into the following. Each line, each row is stored as one record. And also we have a metadata field called line versions, which is incrementing when you modify a line. So how?
Is a line a row?
Yes, a row. So so when you want to update the board, you first, for the first time, you fetch entire board. So you fetch all lines. So you need to read 50 keys from the state because there's 50 by 50, and you get all the lines, but you also get a record of line versions. So this is a metadata for every line or every row that's saying somewhat like what is the last, not like how many times this row was updated essentially. Now to refresh a board, you don't refetch all 50 lines every time because that would be too much keys that you need to read. Instead, you just fetch line versions. So you get one key from the state, and line versions, for example, say, oh, line, or like row number 1 changed and row number 3 changed. So you only need to fetch rows that are modified. Then you remember the new versions of the rows, and next time you update and fetch next versions, you only will need to change the rows that were updated again. So that's how it does this efficiently. It would be possible to rearrange this slightly if locality is more important. So instead of relying on rows, you can rely on somewhat like a cells. So you can break the field into, instead of 50 rows, you can break it into like 5 by 5 cells and maybe have it 100 cells. This way, when you draw locally, you only need to update 4 cells instead of maybe 10 rows. Pixel line is a vector of pixel. Pixel is a color, which is user32, so 4 bytes, and owner ID. So this is the owner ID or account ID from the indices. This is why we assigned a unique index for every account, so we can more efficiently store for every pixel the owner of the given pixel. So by default, the owner is 0, which is this particular contract, which owns all the pixels, and the color is white. So now let's look at the account structure. The account structure is the account ID, account index, so we don't really care because this data can be actually get from the keys of corresponding fetch, but it's easier, just store it internally. Then the balance is U128. So this is number of avocado pixels, well, not pixels, number of avocado tokens. And the precision of one avocado is something like 10 in power of 18. And then finally, we have a timestamp, which in nanoseconds, that is when you last time touched the given account. And we have number of pixels on the board for this account. So why do we need all this information? It is because when you have number of pixels, balance, and timestamp, you can calculate how many rewards you acquired at a given moment. So let's say you had 5 pixels and 1 day passed, then we can say that you acquired 5 avocados for this. And that allows us to update the account in a constant time instead of like refreshing or giving the avocados dynamically every time some moment passed to all accounts. So now what happens if you replace a pixel of someone else? That means that the number of pixels of the owner of this previous owner of this pixel decreased by 1 because you draw on top of this account. It means their rate at which they receive pixels has to change. It decreases. So what we do, we essentially calculate at the given moment how many pixels or how many tokens the account should receive, give them tokens, and set the claim timestamp to the current timestamp. This way, and we decrease the number of pixels, so we updated the previous balance and changed the rate. From now on, they will earn like 1 pixel less. And when you draw something, you need to do the same. We need to calculate how many pixels you had before. So we do this. It's called touch on this account. And this is basically kind of an update account event. So you take the current block timestamp, we calculate the time difference, how much time in nanoseconds passed, and then we update the balance using 1 extra avocado per day. So for example, if you don't have any avocados and don't have any pixels, you can still farm them using 1 avocado a day.
So when someone overwrites someone else's pixel, it updates both their account and that other person's account.
Yes, Yes. And that's why we are limited in how many pixels you can update per batch. So we don't, instead of drawing only one pixel at a time, you can draw multiple pixels, and we'll get to there. And so yeah, so the way we update balance is basically we calculate how much balance we need to give. Then we use a constant, which is reward per pixel per nanosecond, which is a precision, 1 pixel, divided by number of nanoseconds in a day. So let's go to draw. Also, Matt, welcome to this call. We today discussing Berry Club. So
it's a very exclusive club. I feel honored.
Okay, so the way draw works, it takes a vector of pixel requests. Pixel request is a structure that has a coordinate x, y, and a color. Probably can be optimized to pass less data, but it's not very important. There's a validity check, so it should be within boundaries, and the color should be within boundaries. So the way draw works, we first get the account. This thing also has touch. So if the existing account was there, then it will first give all the tokens back to the account and set a current claim. Then we see how many new pixels you want to draw, and we charge the account for this amount of pixels. So we basically just cut it out of balance. We say how many pixels were burned, or like how many tokens were burned for drawing, and then we get a board method called setPixels. It's saying who is the new owner and the list of pixels. And it returns us a hash map which saying how many pixels were deleted for the previous owners and who were the owners. So setPixels works the following way. It goes through all requests. It has a hash map of updated lines, and it uses some Rust method to get an entry, and it basically gets a line, updates the owner and updates the color, gets the old owner, and it saying that the old owner key was deleted, and then it saves the line. I think it's possible to mess it up if you draw the same pixel twice and the owner. Maybe I'll fix it later. I need to check.
I'm interested to hear more about what that bug might be. I'm also curious why the U size, which is maybe a Rust. Like I know what Rust. I know what U size is from Rust, but why use it in this?
U size is used for indices. So when you access an index from the vector, you use U size. Or when you get the length of the vector, non-persistent vector, it also U size. But because of WASM, we want to be like more consistent, and we don't use U size in WASM arguments.
I'm not sure if you're talking about this is a bug or not, but I did notice that when I tried to overwrite my same pixel with the same color, it didn't charge me avocado. So that's actually awesome behavior, and maybe that's expected from what you're showing us here.
So
but
this is probably on a front end, but the bug would be if you overwrite. Actually, it's not. Maybe it's not a bug. But if you overwrite your own pixel multiple times here, then it will say that you draw, for example, 5 pixels, and then you deleted the owners 5 times, which is fine. You're already a new owner here. I think it works okay. Yeah, it seems to be working okay because you just charge yourself multiple times. And we'll here remove your own account, and we say you added, for example, 10 pixels and erased 6 pixels of yourself. So yeah, there's no bug, but it's weird implementation. So basically, yeah, what happens is we modify lines, and we remember. So each line that we modify, we remember it in a temporary map, a hash map. So if one line was modified 5 times, we don't save it immediately. Instead, we iterate on the lines at the end, and we call save line or row. It basically replaces it in the vector and increments the vector of this line. And finally, we return the hash map of owners and how many pixels were erased for every owner, previous owner. So then we go through all accounts except not yours, because your account is updated here. So you added, for example, 5 pixels and replaced one of your own pixels. So you got a total of 4 new pixels, but you will be charged for 5 new pixels. And we save your account, and then we go through all previous owners. And again, using this method, which is which gets account by account index and decrease their number of pixels, and then save their account back to the state. So that's how the math works on drawing and updating the balances. Finally, you can get a leaderboard. Because the front end has the pixel owners, it locally sorts owners by the number of pixels they own. So they don't really need this num account data. And then one by one, it queries all the owners to draw this leaderboard and get their rate. So that was pre-banana release. Any questions on how that worked?
is an avocado a berry? Yes or no?
Yes.
Okay.
Okay, let's go into the branch, the latest branch, and talk about how the migration happened. As you can see, the previous structure had a vector of a legacy account version. The upgrade needed to introduce new balance for bananas, which required to modify account itself, because there could be potentially more than 200 accounts. It wouldn't be possible to migrate them in one transaction potentially, because it may be too much data. So instead, we use a lazy upgrade. So whenever you touch an account, the legacy account, we upgrade it. And ideally, you want to do an upgrade in minimal amount of reads. So you probably want to like read a new account first if it exists. And if it doesn't exist, then you fall back on the reading the legacy account. Because if a new account exists, in a good case scenario, long-term scenario, you only wasted one read or you spent one read. But in upgrade scenario, you will have to do two reads. So you first read the like non-existing or like original, and then you look up the legacy. Oh, you read the latest account, and then you read try to read the legacy account. So the way it's done, we introduce two new fields on the new structure. Number of accounts and a lookup map. You cannot use the vector because vector doesn't have a skipped fields. So like you cannot just have some item that missing and set a length to the larger one. So we needed to switch to lookup map. For this, we need to store a length of this data explicitly as a separate field. Then we renamed the old account into account version of Academy, which is exactly the same structure as was before. And we renamed the old structure to place version of Academy. So this is like a first version, while the new version called just place. Finally, we introduced more balances. So there's renamed mint amount, renamed to bought balances, burn amount to burn balances, and we added farm balances to track how many actually berries were farmed. And this is part of fungible tokens. Also, we introduced a new account structure called upgradable account to prevent mess of like introducing legacy account and this in the future. So upgradable account is enum, which has a version of account. So the same field can store different versions. And then you have a field that converts upgradable account into account that is a structure that we'll use. So this is the most recent account structure. So all code will work with account and not upgradable account. An upgradable account is only needed to read and write. And then we have from account to upgradable account, which will put it at the latest version, which is right now banana account. So if you want to introduce, let's say, a new berry, all we need to do is introduce this version to be something like cucumber account, and then implement a migration from banana account to the latest account version. And then saving is just fine. So the new account version is modified balances. So now the balances is a structure, or it's a vector, which has like two balances instead of one, and introduce the farming preference, which you can pick what you want to farm. Okay, going back to how the upgrade happened is we introduced a new constructor called migrate from version avocado. And it used init because we don't want to read the old state, but the old state should exist already, and we want to write a new state. So we do this with the following. The first line is we read the avocado version of the state, and we say state read is actually Borsch deserializable object, so it will try to read the state of a given type. In this case, option of place avocado, and then we unwrap this into non-option because we want the state to already exist. So if you will call this method right now, this will fail because it will have a mismatch on parsing the state.
Can I interject real quick in case people are watching this video and haven't run into this? If you didn't have the init on top of here, it would try to read the state and match it with kind of like the structs that you have, and you would get state mismatch, and you would kind
No,
of
I think if you don't have init but have mute self, then yes. But if you don't have either kind of static method, I think without init, it will not write the state back to this storage. So you have to manually handle state write.
So you need to do two things. You need it to not. You do need it to write, and you do need it to not try to read.
Yes.
Yeah.
So I manually read. I think it's still an issue the way I did it because if for some reason it still deserializes, then it might be a conflict. But I don't think it does deserialize properly because it would fail on the vector here somewhere. Still probably not the best way to do this. And ideally you would protect against this by saying maybe you will attempt to read the previous state or something. Or like write an extra field which is like, what's the current version? So you will try to read the current version if it already exists and you don't do this. And then you just do a migration from previous version to the new version by put fields in a proper place. So num accounts is like the length of previous accounts. Lookup map is empty with the new field. You introduce vaults for token transfer, migrated balances properly, and reuse the account vectors. And then you have a new. This is in case you want to deploy it freshly to the new version. So this is a standard constructor, but now it constructs a second version. Okay, so this is how we migrated the global state, or like the singleton state of the contract itself. Now we need to be able to migrate accounts. So we have this method, something like get internal account by ID. It was previously just called get account by ID. So what it does, it actually does the following. So it tries to read the index from a new lookup map. If it does exist, which returns an upgradable account, then it converts it to account, to regular account. But if it doesn't exist in the new account, then it will try to read it from a legacy account field, which is, it will read the avocado version of account and convert it to an account through migration. So this part is how you convert from avocado version to account. So you just convert balances and introduce the default farming preferences avocado. So that's how you read.
Sorry, go ahead.
That's how you read it. So
Are you writing it? Are you moving it from one data structure to another?
right. So the moment you save it is when we're gonna write it to the new place. So here's a save account. We first check if this is a new account. Oops. The new account means account index is more than the current one. Then we just need to store it in a structure and also save the new index and increase the number of accounts. It's for sure not a legacy account because it's more than current existing number. And if it is not, then we first try to store it in a new map. And if it didn't exist, so if it's legacy account that didn't exist in a new map, it means it only existed in a legacy vector, but not in the current version of accounts. In this case, we can also free up storage from the vector by making a vector inconsistent. So this is how persistent vector stores data. It has a prefix and prefix A, and then it has of 1 byte, and then it has a length of U64 for the index, which we write index ID. So we recovered the raw key that it used for how the vector stores data, and then we just delete it. We basically say, let's delete it. It will make the vector inconsistent in case we're gonna need to read this value again from the vector, the control gonna panic. But because we never do, if it all works correctly, this works.
That looks really scary.
All right. So the correct way of deleting from vector, you have swap remove, but this will modify the indices of accounts, and I decided not to do this, and it seems possible to do, at least for this case. If we have to do another migration, we will not have a problem because now we're using a lookup map. So a lookup map has a deletion because it can have missing keys, but vector expects all keys to be present.
So correct me if I'm wrong, but I think the beauty of this, because I think I've tried to struggle with like how you do upgradability and like kind of ran into the thought that like, you know, you want to make sure that someone who's paying gas for a transaction is probably only going to use their own gas on their own stuff, and that they're
Mhm.
not like donating gas to like help the upgradability of the contract. Or maybe you do, but maybe you want to have that be like in some sort of like terms of service almost. But it looks like what you're doing here is like it's upgradable, but you're only ever upgrading yourself with your own gas.
Not really, because if you override someone else's account, then you're upgrading their account as well.
Okay. Huh.
But you kind of do an action that touches their account, so somewhat you influence in this. So that's pretty much it from the upgrade perspective. The touch changed a little because bananas are not farmed if you don't have any pixels, so you only get the extra avocado a day, but not for extra banana. And this is a difference when you change a farming preference from avocado to banana. You farm 1 pixel less. I haven't talked about how you buy tokens, but especially with discounts, there's a deal that gets you extra avocado if you buy above 5 near. And the way it works, it just checks if you paid more than 5 near, 5 or more, then it gives you all avocado discounted price. Otherwise, it gives you a default price. And we can talk about how the token contract works, and like that introduced the token contract as well. I introduced a new field, as we discussed in a previous meeting about a vault fungible token. Well, like it was safe-based token, and we had suggestion to rename it to vault. Also, transfer unsafe is renamed to transfer raw because you basically just deposit on a receiver account. And I implemented, basically I just wrote a trade. The comments has to be updated because they were not converted from safes to vaults, but APIs were converted. So you have this trade that you can just copy and paste in your own contract if you want to implement a app 122 for your own token. And then you have impl trade name for place. So I'm implementing this particular trade, so this interface for the contract. So it has much nicer structure to it because now you only need to implement all fields that are required for this particular trade. So let me just delete this to avoid, to be cleaner. So you have methods that you need to implement in order to support a given standard. And if you implement them correctly, then it's good. So I basically copied most logic from the implementation that we had before. I removed short hashes because we don't really worry about the someone abusing it with the storage, because it has a limitation that you cannot register an account for someone else. So if you want to start using this token, you first need to register account for yourself by calling register account. It's not payable. That's how, like, when you first draw, it registered an account for you. But you can also just call a register account. So
I've got a couple
transfer.
high level questions. Before we finish, but I've been talking a lot. I don't know if others have questions, but this is super interesting, and I'm glad to see an implementation of the fungible token contract we saw last week. Does anyone else have thoughts? I think one thing that's really interesting is this is like a case study in terms of sort of like profitability of smart contract. And if you're not under strict audit and want to mention like the gains that you've gotten from Berry Club, I think that'd be really interesting. And like, because you have two things going on. You have the 30% gas fee. People are using it like right now. It's the most like one of the most used apps on mainnet and stuff. So you have the 30%, and then also you have this buying the fungible tokens and whatnot. And
Right.
it seems like from the outset, like that people could actually, like, you're footing the bill for the state, but you're seeing positive returns, correct?
Right. So the total number, I think, if you look at the account, I don't think I withdraw that much out. I moved my original investment for the storage state, and I think I did a few, maybe 10 year out for the something else. So it got, right now it's more than 500, so it's like 527 year. that was used to purchase avocados, and I don't plan to move them because I was working on the next version, which allows you to actually use your bananas, farm bananas, to stake them in order to receive the profit from this contract. So it will basically work similar to staking pool, where you stake bananas, and then based on the total number of bananas staked, the rewards are streaming from Berry Club contract to the next contract and distributed across the participants equally. So for example, if you own 10% of banana staked, then you will receive 10% of rewards. And the way I want to do this is, so this Berry Club contract will, every hour when someone draws for the first time, it will send a transfer which is 1% of liquid balance to distribute rewards. So it will keep some extra for the future state, but also 1% will limit it from draining completely the liquid balance because of decay over time. And it means in the first day of farming, it will probably distribute around 25%, like 20% of the liquid balance, which is around 125 near to the owners of banana who will stake. So I will first introduce the staking tool so people can actually pre-stake, and only after this, once like everyone aware that they can farm or like they can use their bananas, only after this introduce the reward stream. And basically it closes the loop of where now you can draw something by buying avocados, then you stake bananas, like you farm bananas, then you stake bananas, and you get near back that you can use again to buy avocados. And because it's just a demo and I didn't really need it to profit on this, I wanted mostly to test all the variable mechanism around like purchases, then fungible token, and receiving the fungible token on another contract is what's also need to be tested. So we currently only tested just a raw transfer. So I tried it on like using CLI, and I was able to transfer, for example, 2 bananas CLI, and it worked. So next will be to actually test this transfers vault to make sure everything works. And it's slightly simpler implementation because we didn't need to burn tokens if account doesn't exist, because you cannot delete the account on Berry Club. So you can only create new accounts.
And just to be clear, that when that one part where you were actually deleting the state to save a little bit, that was probably not something that average DApp developers would need to do, but you did it because you used a certain kind of data structure instead of lookup map. Is that correct?
Yes, because the vector, well, vector allows you to delete a field, but you cannot really change the index within the vector. So for this one, it was important that the index or the order within the vector stays the same. So, and it seems like vector doesn't expose this particular API. That's why I had to do this manually, because vector doesn't want you to be in inconsistent state.
So if anything, this is kind of an advertisement to use near collections.
Well, vector is a near collection. So yes, but you just need to make sure you think about upgradability a little earlier. So a good tips on this is, one thing that I didn't mention, I introduced human accounts. It's like human readable account. While our account structure uses like Borscht fields, this one actually flattens the balances into two fields and removes the claim timestamp because it's not needed, because you always get up-to-date information. And it creates a third serializable structure, and you have just a converter that maps account to a human account, and then you have a field that returns your entire structure. And staking pools actually uses the same logic. They have a field on them which has a full account information instead of only like manually or like doing this in multiple calls, like get a balance, get a unstake balance, and like stuff like this. So yeah, so on upgradability, if you think that you will need to upgrade an account, I would recommend this type of pattern. So you implement some field, which is enum, upgradable account version 1. It can be like a banana account structure, but you can always rename it. So it can be latest just account. Then you have a converter that converts from previous account to the next account and does this like in a loop. And then you have actual converter back to the structure that just uses the correct enum. So if I had avocado account, for example, here, which would be the correct would be like this, then here I would need to introduce avocado version, and I will get account, and I'll just use account.into, and that's how it will work. So now I can upgrade from avocado version. So let's say I need to introduce a new field. So I will rename this to banana account, and this will be in my new account. So again, I will just use into here, and then introduce a new field. Which will be like this. And here, instead of banana, I will return something like this. So that's entire upgrade that you will need to do. No more mapping from lookup map to a new one, because adding a new enum to Borscht is not creates a conflict with all data. It will work on all data. So that's super simple how you actually doing upgrades. And maybe avocado will first need to be upgraded to banana account, which is fine. But then banana account can be upgraded to the latest account. So you do kind of chain upgrade, similarly how you migrate databases. Okay. Oh, also about gas, it's a shame that I didn't record how much NIR was spent on this particular contract explicitly. So I cannot really tell how much NIR was received from the gas fees versus how much NIR was received from buying explicitly. It's possible to get from Indexer, but not from the account itself.
Not in storage.
And before we close, I want to also present a Wayback Machine, which was built by Vlad. 1 second. Okay, so basically, because this contract was on-chain, you can query historic state from RPC nodes, archival RPC nodes, and this is what Wayback Machine does. It basically, if you click on someone, so I clicked on Vlad here, instead of going to explore now, it goes to a URL Wayback Barry Club.io, which looks at the indexer and queries transaction of a given account, and then renders states that was done by the given account. So like if you do some transactions, after some time it just selects a block height at which you did the transaction, and then it queries this block height for a state of the contract, parses it, and extracts this map. So, and basically it has some stuff, but I think indexer is limited to the number of returns, so it was not returning the latest. And then you can just get it for all users, which is just returns you kind of history of Berry Club drawing up to some point at which either indexer didn't reply or something else. So that's it on the contract and the Berry Club. I would also want to ask Near developers, so if someone builds on Near and wants their contract to be reviewed, then ping me anywhere on Telegram or in like dev channel or Discord, and maybe on the next week we will review your contract and record it and publish it home. Any questions?
Is there going to be a holiday special on avocados?
I don't know. It requires a contract change, so it's not a super simple way of doing some stuff.
I'll take that
Yeah,
as a
we can
maybe.
change the price. It does. It's possible to change the price pretty easily if you just upgrade the contract. But it would not be very fair for people who they're like sweat farmed avocados and bananas in the past.
Fair.
Well, thanks everyone. Hope you enjoyed it. See you next time.